Hello everyone, I'm Serene Mary Joy. I'm a professor at TKM College of Engineering Kerala in India. The research I would like to present today is achieving net zero energy in low-rise residential buildings with a focus on the warm and humid climatic context.
The built environment is the leading source of greenhouse gas emissions, contributing 71% of total emissions globally. The most efficient path to altering the negative impacts of climate change is to create buildings and communities that are net zero energy. Residential building sector is rapidly growing in Indian cities. A zero net energy building produces as much energy as it consumes each year. The main intent is to understand the applicability of a net zero residential building in warm and humid climatic zone. Net zero energy concepts and techniques encourage the use of renewable energy sources to meet the energy requirements of the building. It will basically result in improving the energy efficiency and hence reduction in annual energy consumption. Overall reduction in energy cost of at least 30% will be achieved. Reliable source of power supply if combined with energy storage devices. It is estimated that almost 50% of global energy demand is due to buildings. Therefore, it has become necessary for a change in the global scenario, environment and energy consumption, which led to the approach of green building and demand for alternative renewable energy sources. Net zero energy building is one which uses less water, optimizes energy efficiency, conserves natural resources, generates less waste and provides healthier space for occupants as compared to similar regular conventional building. Some of the main steps to be considered are: first one is to increase the energy efficiency through the help of efficient building construction, efficient system and appliances, operations and maintenance, and change in user behavior or lifestyle. Next step is by addressing remaining needs with on-site renewable energy generation. Talking about the energy and building sector in India, across the world, buildings use about 40% of total global energy and in the process account for approximately 1 by 3rd of greenhouse gas emissions. Of the total electricity consumption in the year 2014 to 15 in India, residential and commercial buildings accounted for 23% and 8% respectively. This increase in electricity consumption in buildings is primarily attributed to the increase in building stock, with the residential build sector expected to increase by at least 4 times from 2012 to 2047. Currently, there are only a very small number of highly efficient buildings that meet the criteria to be called net zero. As a result of advances in construction technologies, renewable energy systems and researches, creating a net zero energy building is becoming more and more feasible. India is facing formidable challenges in meeting its energy needs. It is estimated that by 2031 to 32, the country's power generation capacity of 800,000 megawatt would be required as against the installed capacity of 160,000 megawatt, inclusive of all captive plants in 2020. It is estimated that the country is currently facing electricity shortage of 9.9% and peak demand shortage of 16.6%. So, going solar is one of the main need of the hour to be considered. Every second, our sun produces enough energy to sustain Earth's need for 500,000 years. So, how do we harness this power? The total number of households in India is about 275 million. So, a 3.5 kilowatt rooftop solar system is good enough to meet all the electricity demands of India, and it will take only 6 meter by 6 meter space on each roof. Studies on energy efficiency in Indian residential sector reveals that embodied operational and demolition energy needs to be considered, and the energy use is dependent on building height in terms of number of floors, lifespan, envelope properties and climatic conditions. Building envelope, climatic and site conditions, building materials, water conservation, wastewater recycling, heating, natural daylighting, cooling, ventilation are found to be important parameters for improving energy efficiency in buildings in the comparative analysis done by the previous researchers. Net zero energy building targets energy balance, reduces site energy use through low energy technologies like daylight, natural ventilation, high efficiency HVAC equipments, photovoltaic system and solar hot water system could supply buildings with clean and renewable energy sources. Local building styles, climatic and household lifestyles will impact the demand for each energy service to achieve a net zero energy balance. From the available evidence drawn from the sample of near net zero energy homes in case studies, identifying individual energy service performance targets that when combined with non-regulatory energy loads and on-site electricity generation could achieve a net zero annual operational energy balance. These individual targets for thermal comfort, lighting, water heating and electricity generation are suitable for achieving net zero energy residential units. The suggested actions, which are economically affordable and easy to incorporate, may be seen as practical design standards which are adequate to build residential net zero energy buildings in these regions. Based upon the results, the residential prototype to be created considering the dimensions of spatial, comfort, consumption and generation can be created. The key to designing net zero energy buildings are first reducing energy demand as much as possible and then choosing good energy sources. Lighting energy accounts for more than a quarter of total energy consumption in buildings. It is therefore important to optimize lighting energy used to achieve net zero energy goals. Selecting the right appliances and good usage practices is reducing half energy load. So efficient appliances is the next step. Renewable energy systems are the final step to attaining zero energy goals. Once all possible measures to reduce energy demands are deployed, renewable energy systems must step into balance residual energy demand. Heating, ventilation and air conditioning. Design of a building, climatic zone and operation parameters governs the energy requirement for the comfort system. Reducing heating and cooling loads through passive design and enhancing the efficiency of HVAC systems are steps that are imperative for any building energy efficiency. Talking about the site location, the site is actually located in Kochi, Kerala in India. So this district has a very wet monsoon type of climate. 80 grid dimensions with each grid value of 4 is considered for the simulation in ENVIMAT. The temperature throughout the site is comparatively good as it has a constant range of 24 to 25 throughout the whole site. Ambient values are found for both the readings. Basically, the whole context falls under the warm and humid climatic context of India. Talking about the climatic conditions, this is the psychometric chart for Cochin. So in order to attain comfortable hours, proper shading of the space is actually required, as well as direct evaporative cooling as well as natural ventilation will help in actually achieving comfortable hours or conditions inside the build space as such. And talking about sunshine hours ranges from 4.3 to 9.7 hours per day. And looking at the wind speed analysis, major portion of the site experiences wind speed of about 6.9 meter per second, and major wind direction is from southwest and northwest and from east due to the water body. Still, a very good amount of wind speed is experienced throughout the site, especially near the north and northeast regions is expecting ambient amount. The rest of the site experiences values between 5.4 and 6.9 meter per second of wind velocity. To carry forth the study, first two cases has to be considered. First is the base case scenario and the new or the proposed case scenario. So first, computation of the values of the energy used in building construction has to be found out, and then the energy consumed in building operation has to be found out. Then upon analyzing and comparing these results as such, we get the combined energy used in building construction and building operation. Further analysis and comparison of the results further gives us a design guidelines for net zero residences as such. According to ASHRAE Standard 55, the zone in which most people are comfortable is calculated using the PMV model. In warm and humid climatic zone of Kochi, the comfortable range values between 24 and 29 degrees Celsius. Thus, the thermal comfort is considered to choose the suitable model option based upon WWR values. WWR of 10%, 20%, 30, 40 and 50% are considered and taken into consideration for analysis. In the base case scenario, the window openings are equally distributed on all sides. Material usage like high thermal mass walls, medium thermal mass roof, fenestration, shading, high glazing ratio, high shading coefficient, evaporative cooling, landscaping, courtyard effect, stack effect can actually alter the thermal performance from 1 to 6 degrees Celsius based upon nearly 60 to 65% of the time. Understanding the climatic conditions helps in determining the design interventions required for the region. High potential for passive cooling owing for natural ventilation, all design interventions focused on maximizing this particular potential. Using nature as a resilient device, design evolution came up with multiple options for evaluating functionality, adaptability, energy and comfort. Resulting design is a combination or blend of open coat and a compact shell with a lot of openings for air movement and circulation to enhance ventilation. The open layout allows the occupants to seamlessly transition between the central spaces of the dwelling unit. This was also applied vertically through the stairwell, which enhances stack ventilation. Providing these connections to the outdoors was vital. Design revolves around combating this isolation with nature and community space. Passive techniques like jallis and courtyards enhances daylighting and cross ventilation, which reduces dependency on artificial lighting. Energy efficient lighting and lighting controls for corridors thus reduce the total energy demand of the building. Energy generated through solar panels installed on roof is used for corridor and common area lighting. Indoor lighting is fairly good due to many large openings and light from the courtyard. Front corridor covered by the roof protects inner space from sun and heavy rain. Vertical wooden bars replace the wall panel, allowing wind to pass through large openings. The build precedent of this climate has handled glare by slanting the jali downwards. Glare is caused due to high luminance levels in the clear sky condition. Roofs shade wall in the middle of the day, but let in the lower afternoon sun. Talking about the shading, keep sunlight off the building walls after aiming the building to catch the breeze, the long sides towards the north and south, so the roof overhang shades walls and windows in the middle of the day. The west and east sides were comparatively short to let less of the heat. Low angle morning afternoon sun which heat the walls especially during the hottest sun. Let's look at the comparison between the base case scenario as well as the design case or the proposed case scenario. So these pie charts here shows the approximate distribution of the reduction of the indoor temperature contributed by individual design changes in the case of the base case design and the proposed or the design case. So all these parameters which has an influence upon these distribution of indoor air temperature is actually shown here based upon their influence from the least to the highest category. Again, the life cycle impact of building materials by building system for net zero energy build is again shown here. Based upon the various type of activities that is actually happening or that is actually associated with the building construction, the life cycle impact of building in the base case as well as the design case is comparatively studied and analyzed here. Further analysis of the base case as well as the design case, checking upon the comparison of the results, we get an idea about the materials changed and how it is actually affecting the embodied energy in the base case as well as the design case, and based upon these the lifetime building energy consumption in both these cases is being studied and analyzed. So the results from the analysis showed that the total lifetime energy was reduced from 3974 to 2773 MMBTU, that is a 30% reduction is actually observed in the design case here. This was accomplished by carefully replacing the most energy intensive materials with less energy intensive materials that were also energy efficient, namely the masonry walls, insulation in the ceiling and energy efficient windows. Just like how what you can see in this chart here, the components or the materials that is being changed or that has bring about a considerable change in the values is actually being showcased here. The typical residences we see are responsible for high energy use, high cost and environmental impact. These results represent a first exploration for the development of a method to evaluate the typical strategies for the building envelope for warm, humid climate. This will basically allow a comparison of the design strategies with an integral vision in relation to the energy efficiency and other global concepts including environmental impact and the construction, operation or maintenance cost. In the west facade, for the same area of window, a greater increase of the cooling load is observed. In the west facades, the best solution is to offer walls limiting the areas with windows. Hence, the house having ceiling with common attic has been considered, as it shows slightly better thermal performance, but considering the complexity of construction and safety, this can be neglected. Looking at the design case scenario, the design basically follows an integrated design approach with multi-use spaces, with passive design strategies as well as an outdoor connection. The various techniques or methods which are used to achieve efficiency in water, lighting as well as vegetation is actually shown in these figures. The area allotted per residence falls about 484 meters square with a built-up area of nearly 362 meters square. Overall, upon calculating, the EPI of the residence comes to about 19 kilowatt hour per meter square per year. Energy generated from PV panels is used for exterior lighting and common areas also. The most efficient path to altering the negative impacts of climate change is to create buildings and communities that are net zero. Talking about the climate resilience of the project's carbon footprint is offset in 5 years by carbon sequestering planting panel. Plants with sequestering potential were chosen. The entire crux of landscape is centered around the theme of resilience. Climate resilience has been maximized by increasing the on-site permeability and establishing multiple filtration and on-site recharge points on site. With network of interventions like bioswales, rain gardens and detention ponds, the nexus of blue-green infrastructure avoids landscape fragmentation and sets up the flood-resilient environment. It also reduces inconvenience caused by annual flood as second floor level was always higher than the peak. Gutters and downpipes channel water from the roof to the tank. Screens, first flush system and filter components which remove debris and dust from the captured rainwater before it goes to the tank. Roof water from rain is channeled through pipes, passed through a series of filters and collected in the water tank. Grid pavers are kept all along the site to prevent soil from eroding and to hold soil in its position. On to the waste management. The chart here shows the type of waste generated on site and its segregation process. The space requirement shall be calculated so as to carry 2.6 kg of waste per household in the case of a family of 4 persons and an average density of waste say 0.5 tons per meter cube. So quantity of waste generated by a house is calculated by 0.2 into number of persons in the house. On an average on daily basis, every person produces 1.8 kg waste every day, that is 0.0018 tons. So considering this as the average, per day it produces 1 cubic meter of biogas. Portable biogas plants are built using fiber reinforced plastic and it can be fixed in a very small area. Recycling grey water with the roots of plants like canna can give a perennial source of water. As grey water trickles down, it gets purified by the action of the canna roots and the natural microbes present in the soil, and the treated water enters the groundwater table. Plants like Canna indica, Hedychium and Heliconium supply oxygen to the soil in the root zones. Using this oxygen, soil bacteria break down organic compounds in grey water and render the water clean. So, talking about the site level water management, the total water demand is actually met by rainwater harvested, recycled grey water and fresh groundwater. Out of the total water demand, 36% is actually met by the rainwater harvested, 30% by recycled grey water and 34% by fresh groundwater. So this diagram here shows the water networking system that should be adopted within the site. So the groundwater table level lies within the range of 5 to 10 meter depth. Gutters and downpipes channel water from the roof to the tank. Screens, first flush system and filter components which remove debris and dust from the captured rainwater before it goes to the tank. Delivery system is usually gravity fed or pumped to the end use. And talking about filters and other methods is actually used for treatment as well as purification purposes. Roof water from rain is channeled through pipes, passed through a series of filters and collected in the water tank. And talking about this water networking system as such, portable rainwater catchment area is actually accomplished with the help of rain catchers, building rooftop and parking rooftop. And coming on to detention ponds within the site level, site water drains as well as rainwater harvesting storage overflow is actually used to help achieve this. Conscious choices of sustainable lifestyle can help reduce household consumption by up to 730 liters per day. Further, efficient measures such as low flow fixtures, micro drip irrigation and native plants reduce the consumption on site. Owing to these measures, the National Building Code's minimum requirement of 135 liters per day can be reduced up to 80 liters per day per person. So, overall, 70% of the total occupant demand in a residential unit is met with portable rainwater and filtered grey water. Talking about the emissions per capita will rise from the levels of 1.7 tons per capita to 3.7 tons per capita in 2030 and further to 5.8 tons per capita for the supply mix as generated by the model. The graph here shows the greenhouse gas emission projections in India, and it is clearly evident the greenhouse gas emissions per capita is rising exponentially over the years as projected. The built environment is the leading source of greenhouse gas emissions, contributing 71% of the emissions globally. So moving on to the supply side management. The supply side management is actually analyzed and achieved by studying the annual energy use and the renewable energy that can be generated within the site. So as to compute the annual energy use, the baseline site energy use has to be computed based upon site energy use reduction, design or operational energy required, the site energy use as well as use by energy source. After computing these values, renewable energy that can be obtained within the site has to be computed based upon its potential from photovoltaic cells, renewable energy located within building footprint as well as renewable energy located within the site. Further, the PV tilts comparison study to analyze the performance factor of these modules has to be studied. So a tilt of 10, 20 and 40 degree tilt has to be studied, and based upon that the performance factor for 0 degree tilt, 20 degree tilt and 40 degree tilt is obtained. So number of modules as well as the annual energy generation from these PV modules of 20, 40 and 0 degree tilt is hence achieved accordingly. So the total roof area of each module or each dwelling unit comes around nearly 380 square meter. So the total roof area mentioned for solar panels comes around nearly 200 square meters. That is nearly 53%. So based upon that, the annual electricity generation from solar plant varies between the range of 20,400 kilowatt hour to 76,500 kilowatt hour. So that is the potential range of energy generation from solar plant. So this basically reduces the carbon dioxide emissions, which is actually mitigated, is actually falls around 627 tons. So this installation will be somewhat equivalent to planting 1,004 trees over the lifetime. After dealing with supply side management, we'll look upon the demand side management. So demand side management for achieving net zero energy balance mainly deals with three stages, that is the net zero site energy combining the building site energy use, and net zero site energy combining the building site energy use within the building level as well as within the site level. So classifying these as categories A, B and C. Under classification A, we get a balance of 30,600 kilowatt hour just by as the building site energy used. So by considering the site the energy which is produced within the site level, we get a balance of 8,870 kilowatt hour. And whereas combining the building site energy used within the building level as well as the site level, we get an again balance of 8,870 kilowatt hour, which leaves us with the surplus amount, that is plus 8,870, which in turn turns out to be a net positive building. Once this prototype is created based upon the net zero energy balance which has been achieved just now, it is actually a globally scalable prototype. So this design basically caters to issues such as ventilation and air movement, promote heat loss and resist heat gain, thermal comfort or cooling and dehumidification, very high solar flux as well as solar radiation. So basically it is scalable in similar geoclimatic zones which has warm and humid climatic conditions. So the residential prototype has been created considering the four dimensions of spatial, comfort, consumption and generation. The performance analysis indicate the prototype works better than the conventional cases, and net zero balance is achieved up to 100% in terms of energy, water and waste. Effective shading has reduced solar gain to 1,320 kilowatt hour per year, with an average monthly reduction of 100 kilowatt hour in the final design prototype. And 96% of the total occupied hours are found less than 29 degrees Celsius, which is actually falls between the comfort range in Cochin. The estimated EPI falls around 19 kilowatt hour per square meter per year, which shows considerable reduction from the contemporary cases of EPI of 96 kilowatt hour per square meter. The installation of the various methods initially would be costly, but in the long run, the owner of the building would save money on their energy bill. More importantly, in the scarcity of natural resources, we would be providing a self-sufficient, energy-saving, non-polluting zero-energy building. Based upon the results, the residential prototype to be created considering the dimensions of spatial, comfort, consumption and generation can be created. Thank you.